Welcome to the 31st explainer in our series on research methodology, titled Experimental and Non-Experimental Research Design. Okay, I want you to imagine for a moment that you are a detective. You've just been handed this incredibly complex, totally baffling case, and you need to uncover the truth. Now, you wouldn't just wander out into the street looking for clues at random, would you? No, of course not. You need a strategy. Well, in the world of academic and scientific investigation, that overarching strategy is your research design. Today, we are going to explore the two most fundamental master plans a researcher can use to crack a case: experimental and non-experimental designs. By the end of this explainer, you are going to know exactly which detective hat you need to wear for your next big investigation.
So, here is our syllabus for today's module. It's basically a roadmap to help us organize these two massive methodological worlds. We'll be covering 1. The research blueprint, 2. Experimental research designs, 3. Non-experimental research designs, 4. Comparing the two designs, and finally, 5. Ethics, validity, and pitfalls. Let's just jump right in.
Section 1. The research blueprint. Okay, let's dive into this. Like we said, every great detective needs a master plan before taking the field, right? Well, every great researcher needs a blueprint. You literally cannot build a solid study without one. The eminent methodologist C.R. Cathari actually defined research design as, and they quote, "the arrangement of conditions for the collection and analysis of data in a manner that combines relevance to the research purpose with economy and procedure." Now, I know that sounds like a bit of a mouthful, but the crucial takeaway here is this. A design isn't just some boring technical checklist. Actually, scratch that. It's way more than a checklist. It is the logical structure, the bridge really, connecting the specific problem you want to solve with the exact evidence you need to solve it. It ensures your study actually answers your question and does so without wasting your time, your money, or your effort. Just imagine surveying 1,000 people, spending months on data entry, only to realize you asked the completely wrong questions to solve your case. Yeah, no way. That is exactly what a good blueprint prevents.
Section 2. Experimental research designs.
All right, let's step into the highly controlled laboratory. Welcome to the controlled sting operation. This is the world where researchers aren't just sitting back and watching things happen. They are actively pulling the strings. They want to prove, without a shadow of a doubt, exactly who or what caused a specific outcome. To pull off this kind of sting operation, you need what we can almost consider the holy trinity of experimental design, plus a couple of other really vital additions. First up, we have the manipulation of the independent variable. This means you are actively doing something to the subjects. Second, the measurement of the dependent variable. You need to see exactly what changed after you did that thing. Third, control of extraneous variables. This is absolutely crucial. This means making sure outside noise, like, say, the temperature of the room or the time of day, doesn't ruin your data and skew your results. Fourth, random assignment to participants. This ensures your groups are completely fair and equal right from the starting line. And finally, you need comparison or control groups to serve as your absolute baseline.
Let's slow down for just a second here to really hammer home this single defining concept. If you remember literally nothing else about experimental research today, remember this: the main feature is manipulation. You, as the researcher, actively introduce a treatment, an intervention, or a specific condition, and then you closely examine the resulting change. Think of it like this. You aren't just quietly watching a plant grow in a forest. No, you are actively giving one plant a brand new experimental fertilizer, and you are deliberately withholding it from another plant just to see what happens. You are forcing a condition to observe an outcome.
But we have to realize that not all experiments are created equal, right? Let's look at how this builds a hierarchy of control. At the very top, we have the gold standard, true experimental design. This one has the whole shebang: manipulation, control, and random assignment. It gives you the absolute strongest evidence for causality. Then, right in the middle, is quasi-experimental design. It has manipulation, which is great, but it lacks full random assignment. This actually makes it highly practical for working with real-world groups. And down at the bottom, we have pre-experimental design. This is the weakest form, often lacking control groups entirely. Honestly, it's really only useful as a pilot study to test the waters before a real investigation. Why is it so weak? Well, think about it. If you only measure a group after an event occurs, without any baseline or a control group to compare them to, you can never be entirely sure the event actually caused the change.
And this brilliantly illustrates the tension between the perfect sterile lab and the messy real world. In a true experiment, you can randomly assign students to two completely different teaching methods just to see which one works better. But let's be real. In reality, school principals rarely let researchers shuffle their students around like a deck of cards just for an experiment. That's exactly where quasi-experimental design comes in to save the day.
We lose that perfect random assignment, relying instead on naturally existing groups, like using Classroom A for the new teaching method and Classroom B for the old method. We are still manipulating the teaching style, but we have to be incredibly careful about pre-existing differences between those two classrooms that might muddy our data.
Section 3. Non-experimental research designs.
Okay, time to shift our narrative arc entirely. We are leaving the highly controlled lab and stepping out into the wild as the natural observer. This is the realm of non-experimental research designs, and we use these when manipulation is impossible, unethical, or just plain unnecessary. As the sociologist Earl R. Babby so perfectly put it, many social research questions require observation of naturally occurring conditions rather than experimental manipulation. You know, sometimes a detective shouldn't set up a sting operation. Sometimes they just need to act as a shadow, quietly observing subjects in their natural habitats without interfering at all. For example, if you want to study the effects of poverty on childhood education, well, you obviously cannot ethically assign students to be poor. You have to observe the world exactly as it already is. And because the natural world is so incredibly diverse, our non-experimental tools have to be diverse too. Let's break these down real quick. Descriptive designs, they simply paint a factual, accurate picture of what exists right now. Correlational designs hunt for statistical patterns between variables, like seeing if a person's height and their shoe size tend to rise together. Causal comparative or ex post facto designs look backward in time to compare naturally existing groups. Think about analyzing outcomes for students who already attend private versus government schools. Surveys ask the masses for their opinions through carefully structured questionnaires. Observational designs systematically watch behavior unfold in real time, kind of like a researcher sitting quietly on a park bench to study how children share toys on a playground. And case studies? Oh, they zoom all the way in for an intensely detailed look at a single complex phenomenon, like one specific community's response to a massive natural disaster.
But here is the absolute golden rule of the natural observer. Correlation does not prove causation. I'll say it again, correlation does not prove causation. Just because two things move together in your non-experimental data, like say the amount of time spent studying and high test scores, that does not automatically mean one caused the other. Maybe highly motivated students just tend to study more, and it's actually their underlying pre-existing motivation that is causing those high grades. Without experimental manipulation and tight control over all those pesky extraneous variables, you are finding fascinating patterns for sure, but you are not finding undeniable proof of cause.
Section 4. Comparing the two designs.
So, we've explored the lab, and we've explored the outdoors. Now, what's really interesting about this slide is that it's time to put these two blueprints in the ring together for a head-to-head matchup. As we draw the battle lines here, I want you to constantly signpost back to this main question. Are we manipulating, or are we observing? Experimental design deliberately manipulates, non-experimental naturally observes. Experimental loves random assignment, non-experimental rarely uses it. Because of this, experimental operates in heavily controlled environments and offers incredibly strong causal inference. Non-experimental, on the other hand, operates in the messy real-life world. That makes its causal claims naturally weaker, yes, but its ability to describe complex, authentic, everyday relationships is absolutely powerful.
So, what does this all mean? The crucial point is that neither design is universally superior. As Creswell and Creswell remind us, your choice of design should depend entirely on your specific research problem and the exact type of evidence you need. Think about it. A good detective doesn't use a magnifying glass to dust for prints, and a good researcher doesn't use a controlled experiment to explore historical trends. You must simply choose the right tool for the specific mystery you are trying to solve.
Section 5. Ethics, Validity, and Pitfalls. As we near the end of our investigation today, we really need to talk about the rules of engagement. Because choosing a research design isn't just some technical decision you make in a vacuum, it carries immense responsibilities. A major part of this responsibility comes down to validity, meaning how truthful and accurate are your findings really? We are constantly balancing two types here. Internal validity asks, did variable A truly cause variable B without any outside interference? Experimental designs usually win this battle, hands down. But external validity asks, can we confidently apply these findings to the real world outside of our artificial lab? And because non-experimental designs take place in natural settings, they almost always win the prize for external validity. It's a literal balancing act. Too much control makes a study feel totally artificial, but too little control makes its findings highly uncertain.
And then, of course, there are the ethical boundaries. When we play with variables, especially in experimental designs, we literally hold the well-being of our participants in our hands. The Belmont Report lays out an excellent ethical compass for us to follow here. First, respect for persons. This means strict, voluntary, informed consent at all times. no exceptions. Second, beneficence. This means we must maximize the benefits of the research while absolutely minimizing harm. For example, if you are testing a new educational intervention and you spot a negative trend where some students are actively falling behind, you stop the study early and you offer resources. You never expose participants to harmful conditions just to observe the effects. And third, justice, meaning the fair selection and equal treatment of all participants. Let me be clear, a researcher's data is never, ever more important than human dignity.
Okay, to ensure you design an absolute masterpiece rather than a methodological disaster, you should actively avoid these very common pitfalls. Number 1, making hard causal claims from non-experimental survey data. Seriously, don't do it. Number 2, calling your study an experiment when you didn't actually manipulate anything or use a control group. The words we use in methodology really do matter. And number 3, assuming an experimental design is always the best choice just because it feels more rigorous. It isn't always. You have to align your statistical methods, your bold causal claims, and your entire analytical mindset strictly with the structural blueprint you actually chose to build.
So, I want to leave you with this final, provocative thought. Which blueprint does your next research question truly demand? Remember, every groundbreaking investigation starts with the right plan. Whether you are actively manipulating variables in a controlled sting operation or observing patterns quietly from the shadows, your design is the ultimate key to uncovering the truth. If you found this breakdown helpful for your own research journey, please take a second to like, comment, share, and subscribe to this channel so we can keep bringing you clear, focused explainers just like this one. Thanks so much for learning with us today, and happy researching.